In this video, we're going to look at graph theory questions which can be answered by a different concept, Hamilton paths and circuits. Okay, so let's consider a pizza delivery person. This is our second type of graph theory question. This pizza person is concerned with going to every location exactly once in the most efficient way possible. All right, so his delivery locations, we can think of those as the vertices, and the routes we can think of as the edges. Right. Now remember, for our previous graph theory question with the mail carrier, we had a different definition of efficiency. Now maybe in this case, right, maybe we're not concerned with covering every edge exactly once. Right? Maybe we're actually concerned with just getting to every location exactly once. All right, so if that mail carrier was interested in walking the least amount of time, then maybe he was okay with sort of returning to the same house a couple times, as long as he didn't repeat a sidewalk or a road more than once. But this pizza delivery guy, maybe he's concerned with hitting all of the locations exactly once, and he's okay with skipping some of the roads between them. All right, so one of the questions in graph theory is just to decide how to phrase the problem. Which of these solutions are we interested in? And sometimes it's more than one. But in this case, let's try finding an efficient route using a different definition of efficiency. Okay, so we'll look at Hamilton paths and circuits and find optimal solutions, meaning in this case efficient routes, using three different methods. So a path on a connected graph that passes through every vertex exactly once is called a Hamilton path. Okay, so it's not every edge anymore, it's every vertex. A Hamilton path that begins and ends at the same vertex but passes through all other vertices exactly once is called a Hamilton circuit. Okay, so definitely a circuit will hit one of those vertices, the beginning and ending one, more than once. Okay, but that's okay, as long as all of the other ones are exactly once. Okay, so let's find a Hamilton path that begins at vertex A for this graph. So what are we looking for? We need a path. Okay, so we can't repeat edges. Can't repeat edges, that's what it means to be a path. It's got to be a Hamilton path, meaning every vertex, but exactly once. Every vertex, every vertex exactly once. Okay, and we have to start at vertex A. Okay, so see what you can come up with. There are multiple options. Here's one of them if we just go alphabetically. A, B, C, D, E. That's a path that crosses every vertex exactly once. Okay, so A, B, C, D, E. Now, is there something that's similar to Euler's theorem that would help us to determine if there are or are not Hamilton paths or circuits? Well, in the case of Hamilton paths, no. All right, we have some methods for just jumping in and trying to find one, but we can't determine ahead of time whether or not there's going to be a Hamilton path. However, we do have a condition that guarantees the existence of a Hamilton circuit. All right, and this condition depends on complete graphs, so we need to know what those are. Complete graphs are graphs that have an edge connecting every pair of vertices. All right, so if you look at these two figures, this first one, right, notice basically what we're trying to say is that every vertex needs to be connected to every other vertex. All right, so vertex A needs to be connected to B, C, E, and D. B connected to A, D, C, and E. Okay, and so forth. All right, and that one is connected. So this is complete. This is a complete graph. The vertex on the right, or the graph on the right, right, this is not complete. Right? If we looked at vertices B and D, for example, there is no edge that connects that pair of vertices. Okay? So every vertex is not connected to every other vertex. So this one is not a complete graph. Now there is an easy way to tell if a graph is complete. A graph with n vertices is complete if it has no loops and every vertex has degree n minus 1. Okay, so if we looked at, we'll go back and look at the larger picture. Okay, of these two graphs. Alright, so n stands for the number of vertices in the graph. Alright, so if we have A, B, C, D, and E, that's 5 vertices. Oops. Okay, 5 vertices. And we're checking to see if each degree is n minus 1 or 5 minus 1. Okay, so each vertex needs to be degree 4. Okay, so A is degree 4, so is B, so is C, so is D, so is E. And we have no loops, so that makes this a complete graph. Right away I can tell that this graph is not complete. There are 4 vertices, so each degree should be 4 minus 1 or 3. And that is the case for A and C, but it's not the case for B and D. We had that missing edge. Okay, how about figure 1439, this graph? Okay, there are 5 vertices, so there should be degree 4 for each vertex. And right away I can tell that that's not the case. A and C, for example, are only degree 2, so this is not a complete graph. Alright, does a Hamilton circuit exist? So here's our condition. Every complete graph with more than 2 vertices has a Hamilton circuit. Furthermore, the number of Hamilton circuits in a complete graph with n vertices is n minus 1 factorial. Alright, so we're using the factorial symbol that we've talked about when we looked at probability and counting methods. Okay, so let's say we had a complete graph with 5 vertices. Okay, then we know that each vertex is degree 4. Okay, and then the number of Hamilton circuits is n minus 1 factorial. So that would be 5 minus 1 or 4 factorial, okay, which is 24. So there would be 24 Hamilton circuits. And then here's a note. When we're counting those 24 circuits, 2 Hamilton circuits are considered to be the same if they pass through the same vertices in the same order, regardless of the vertex where they begin and end. Alright, so if you get a different count, you probably counted something twice or not at all. So let's say that I had, we'll look at this graph real quick. Okay, A, B, C. This is complete. Okay, it's got 3 vertices. The degree of each vertex is 2. Okay, and there are no loops, so I know that it's complete. And the number of Hamilton circuits should be 2 factorial, which is 2, right, or just 2 Hamilton circuits. So, for example, A, B, C, A, that's a Hamilton circuit. Okay, A, C, B, A, that's a Hamilton circuit. Right, what if I start at B? B, C, A, B. Okay, that's one. Okay, how about B, A, C, B? That's one. It's a, and so forth. All right, so where are we getting all of these from? There should only be 2 Hamilton circuits. All right, well, these guys are actually just doubles of the ones that we already found. Okay, so notice this first one, A, B, C, A, starting at A, going to B, going to C, going to A. Okay, it kind of makes this circuit heading in this direction. Okay, so this one here, this is the same vertices, B, C, A, and B, and it is in the same order. Okay, so I hit B, then C, then A, then B. Okay, so if I ignore where this begins and ends, okay, whether it's A or B, then notice that I could still follow this kind of clockwise path around through those vertices. Okay, so that's the same one. Now this second one is distinct. All right, this is different. ACBA, that goes in a different order. It's going the opposite direction. Okay, so A to C, and then C to B, B to A. All right, so we have kind of like a clockwise and a counterclockwise, or sometimes you'll have a forward and a backward, and those are like your two circuits. All right, how many Hamilton circuits are there in this graph? Okay, so we have 5 vertices. So that means that, if this is complete, which it is, all the degrees are 4, then the number of Hamilton circuits, that's that little formula, n minus 1 factorial. So there would be 5 minus 1 factorial, or 4 factorial, or 24 Hamilton circuits. Okay, we'll stop there, and in the next video we'll start looking at how to find Hamilton paths and circuits.